Welcome back, everybody, to the Deep Dive. And today we've got something special straight from our AI.Code.Cast community. Maximizing profit with job scheduling.
Ooh, yeah.
You know, that's classic problem. Really puts those algorithmic skills to the test.
Yeah, it's a fascinating one, and it's so relatable,
Yeah.
even outside the world of coding. So imagine you're a freelance coder,
Okay.
or anyone really, with a flexible schedule.
Yeah.
You've got a bunch of potential gigs lined up. Each gig has a start time and end time, and the profit you'd make if you completed it.
I like it.
But the catch is you can only work on one gig at a time.
Okay, so it's like you've got invitations for like the ultimate networking event.
Yeah.
But instead of maximizing handshakes, we're maximizing profit here.
Exactly. The goal is to figure out which combination of gigs is going to earn you the most money.
Right.
Taking those pesky time conflicts into account.
So it's not just about picking the gigs with the highest individual payouts.
Right.
There's got to be a strategy here to
Absolutely.
weave these together,
Yeah.
maximize that overall profit.
Let's say you have a high-paying gig that takes up your entire day,
Okay.
but you could potentially fit in two shorter, lower-paying gigs
All right.
during the same time period.
During that same time period.
It might be more profitable to go for the shorter gigs, even if they seem less appealing at first glance.
I see. So this is where our coding brain's got to kick in, right?
Precisely.
Got to sift through these possibilities.
Yeah.
Pinpoint that most lucrative schedule.
And the first approach that might come to mind is the good old brute force method.
Ah, yes, the classic try everything and see what sticks approach.
Exactly. In this case, brute force would involve generating every single possible combination of gigs
Right.
and then calculating the total profit for each combination.
Right.
The combination with the highest profit wins.
Sounds straightforward enough,
Right.
but I have a feeling there's a catch.
Well, you're right. While brute force can work for very small sets of gigs,
Yeah.
it becomes incredibly inefficient as the number of gigs grows.
I can imagine.
Imagine having to evaluate the profit for every possible subset of 100 gigs.
Oh, wow.
That's a recipe for computational meltdown.
Yeah, my laptop is like bursting into flames just thinking about it.
Yeah.
So brute force is out of the question for anything beyond a handful of gigs.
Right.
What other options do we have?
Well, this is where things get really interesting.
Okay.
The AI.Code.Cast community came up with a bunch of clever solutions that use more sophisticated techniques.
All right, spill the algorithmic beans. I'm ready to upgrade from brute force to something a bit more elegant.
One approach that really stood out to me uses dynamic programming.
Dynamic programming. I've heard the term, but honestly, it still sounds a bit intimidating.
Right.
Could you break it down for us?
Yeah.
For us mere mortals.
Dynamic programming is all about breaking down a big, complex problem into smaller, overlapping subproblems. And the key is that we solve those smaller problems once, and we store the results.
Right. So we don't have to waste time recalculating them over and over again.
Gotcha.
It's all about efficiency.
Okay. I'm starting to see the appeal here.
Yeah.
But how does this apply to our job scheduling puzzle?
So let's imagine our gigs are represented in a nice, organized way, perhaps as an array, with each element containing the start time, end time, and the profit for a particular gig, instead of trying to solve the entire problem at once.
Right.
Finding the optimal schedule for all the gigs, we break it down.
Break it down,
We start by figuring out the best schedule for just the first gig. Then we figure out the best schedule for the first two gigs. Building upon the result we got for the first gig.
Gotcha.
And so on.
So we're building a tower of solutions.
Yeah.
One level at a time.
Yeah.
Using the solutions from the lower levels to support the higher ones.
That's a great way to put it.
I like that.
Each level of our tower represents a subset of gigs.
And the value we store at each level is the maximum profit achievable from that subset.
Yeah.
And because we're reusing the results from the lower levels, we avoid redundant calculations.
That's pretty clever.
Right.
I can already see how this would be much more efficient than brute force.
Exactly.
Especially when we have a lot of gigs to consider.
And there's another key aspect of dynamic programming that's crucial for this problem.
Let me guess. It involves sorting, doesn't it?
You read my mind. To make this dynamic programming approach work its magic, we need to first sort our gigs by their end times.
That makes sense.
Right.
If we process the gigs in the order they finish,
it
becomes much easier to determine which gigs are compatible.
You got it. Sorting is our secret weapon for efficiently building that tower of solutions.
Okay, I'm following so far.
Yeah.
We've got our gigs neatly sorted by their end times.
Right.
We're ready to start building our dynamic programming tower of profit.
Okay.
What's the next step?
Here's where things get even more interesting.
Okay.
For each gig, we need to make a decision.
Okay.
Do we include it in our schedule or not?
So it's like a constant game of 2 gig or not 2 gig.
Exactly. And to make that decision, we need to look back at the gigs that end before the current gig starts.
Yeah.
Remember, we can't have overlapping gigs in our schedule.
Right. So we need to find a gig that leaves enough time for the current one to fit in.
Yeah.
It's like finding a compatible puzzle piece.
Perfect analogy.
I like it.
Now, here's the crux of the dynamic programming approach.
All right.
To decide whether to include a gig, we compare 2 things.
Okay.
First, we consider the profit we'd get if we included the current gig.
Right.
Adding its profit to the maximum profit achievable from the compatible gigs that came before it.
So we're basically saying, if I take this gig, what's the best I can do with the remaining time?
Precisely.
Love it.
The second thing we compare is the maximum profit we could achieve.
Yeah.
From the compatible gigs that came before it without including the current gig.
So it's like saying, if I skip this gig, am I still on track for the best possible profit?
You've got it.
All right.
We weigh those 2 options.
Okay.
And pick the one that yields the higher profit.
Makes sense.
This decision then informs the solution for the next level of our dynamic programming tower.
Okay, so it's a series of strategic comparisons, building upon the solutions we've already found for the smaller subproblems.
Exactly.
I'm really starting to see how dynamic programming tackles this scheduling challenge.
It's a beautiful example of how breaking down a problem and reusing solutions can lead to a much more efficient algorithm.
I like it.
But wait, there's more.
My algorithmic senses are tinkling.
Okay.
What other tricks do we have up our sleeves?
Oh, right.
Yeah. All right, my brain is buzzing with all this dynamic programming talk, but I have a nagging feeling there's a piece of the puzzle we haven't addressed yet. How do we actually find those compatible gigs that end before the current gig starts?
Right.
Are we stuck doing a linear search through all the previous gigs?
That's a great question. You're absolutely right.
Yeah.
A linear search would defeat the purpose of using dynamic programming in the first place.
Right.
It would make our algorithm much slower.
Especially when we have a large number of gigs to schedule.
Exactly.
So there has to be a more efficient way to pinpoint those compatible gigs.
Yeah.
What's the secret weapon?
The secret weapon, my friend, is binary search.
Okay.
Remember how we sorted our gigs by their end times?
Yeah.
That sorting was not just for organizational purposes. It was a strategic move to unlock the power of binary search.
Okay, I'm starting to see the connection.
Yeah.
Binary search is all about quickly finding a specific value in a sorted list.
Right.
It's like looking up a word in a dictionary. You don't have to flip through every single page.
Exactly. In our case, for each gig we're considering, we can use binary search to efficiently find the latest gig that ends before the current gig starts.
Brilliant.
We don't have to waste time examining gigs that end after the current gig.
Yeah.
They're simply not compatible.
I see. So binary search helps us zoom in on the compatible gigs without having to wade through the entire list.
Right.
It's like having a fast forward button.
Precisely.
For our gig selection process.
And the beauty of binary search is that it's incredibly efficient.
Yeah.
The time it takes to find a compatible gig grows very slowly, even as the number of gigs increases dramatically.
Right.
It's a logarithmic time complexity.
Music to any coder's ears.
Exactly.
So we've got this dynamic programming approach working in tandem with binary search. It's like a dream team of algorithms, each playing its part to maximize our profit potential.
I like it.
But I'm curious, are there other ways to solve this job scheduling puzzle?
Absolutely. The AI.Code.Cast community is a hotbed of algorithmic ingenuity, and they came up with a bunch of other clever solutions. One that I found particularly intriguing uses a binary search tree.
A binary search tree. Now, that's a term I haven't heard in a while.
Right.
Can you give us a quick refresher on what those are all about?
Sure thing. A binary search tree is a special kind of data structure that's, well, shaped like a tree.
Yeah.
Each node in the tree represents a value, and it can have up to 2 children, a left child, and a right child.
Okay.
The key property of a binary search tree is that the value of the left child is always smaller than the parent's value.
Okay.
And the value of the right child is always larger.
Okay. I vaguely remember this from my data structures class.
Yeah.
It's like a tree that's always neatly sorted.
Right. You got it. And that sorted structure is what makes binary search trees so powerful for searching and retrieval.
Yeah.
We can quickly find specific values without having to traverse the entire tree.
So how do we apply this tree-like structure to our job scheduling problem? I'm having trouble visualizing how it fits in.
Imagine this. We construct a binary search tree where each node represents the end time of a gig. In addition to the end time, each node also stores the maximum profit achievable up to that end time.
Okay, so it's like each node is a snapshot of the best possible profit we can earn to that particular point in time.
Now, when we're considering a new gig with a certain start time, we can traverse the binary search tree to find the node with the largest end time that's smaller than our gig's start time.
So we're essentially looking for the rightmost node in the tree that's still compatible with our gig start time.
Right.
Similar to how we used binary search before.
Exactly. And because the tree is sorted by end times, we can efficiently find that compatible node.
Right.
Without having to examine every single node in the tree.
That makes sense. So the binary search tree is like a map that guides us to the most profitable path, ensuring we don't miss any lucrative opportunities along the way.
It's like having a GPS for profit maximization.
I like it.
And just like with dynamic programming, once we've found that compatible node which holds the maximum profit achievable up to that point, we can make our decision, include the current gig, or move on to the next one.
Okay, I'm starting to see the pattern here.
Yeah.
The core logic of deciding whether to include a gig seems to be the same across these different solutions. That's probably a good idea. We've covered a lot of ground already, and binary index trees sound like they deserve our full attention.
Yeah.
So we'll be back in the next part to unravel that mystery.
All right.
And wrap up our deep dive into job scheduling. Stay tuned. Welcome back to the deep dive. We've been exploring all these different ways to tackle this job scheduling problem, and I'm really eager to hear about this mysterious binary index tree solution you mentioned.
It's definitely one of the more advanced solutions, but it's also incredibly efficient. It leverages a data structure called a binary index tree, or BIT for short, which might sound intimidating, but it's surprisingly elegant once you grasp the concept.
Okay, my brain is ready for a challenge. What are these BITs all about?
Imagine you have a list of numbers, and you need to perform two operations frequently. Finding the sum of numbers within a specific range and updating a specific number in the list. The BIT is designed to handle both of these operations incredibly quickly.
I can see how that might be relevant to our job scheduling problem.
Yeah.
We're essentially dealing with ranges of time
Exactly.
and trying to maximize profit within those ranges.
In this case, we can use a BIT to efficiently keep track of the maximum profit achievable up to a certain point in time. Think of it like a supercharged array that allows us to quickly answer questions like, what's the best profit I can get up to this particular time slot?
Okay, so it's similar to how we use the binary search tree to find the maximum profit achievable up to a compatible gig's end time.
Yeah.
But the BIT is even more efficient for these types of queries and updates.
You got it. The BIT uses some clever bit manipulation techniques under the hood. But the key takeaway is that it allows us to manage profit information related to time ranges with lightning speed.
That's pretty impressive. I'll admit the inner workings of a BIT are still a bit fuzzy for me.
Sure.
But I'm definitely intrigued by its potential.
It's a great example of how a data structure that might seem unrelated to a particular problem can actually be the perfect tool for the job.
Speaking of tools for the job, we've got one more solution to cover. The one that combines binary search with memoization.
Right. This one uses a recursive approach to explore different combinations of gigs, but memoization helps us avoid redundant calculations and keep things efficient.
Okay, remind me how memoization works again. It's all about storing results, so we don't have to repeat the same work,
Exactly. Imagine you have a function that performs a complex calculation. Memoization is like creating a cheat sheet for that function. Whenever the function is called with the same inputs. Instead of doing the whole calculation again, it simply retrieves the stored result from the cheat sheet.
So it's like having a handy lookup table for our function's output.
Exactly.
That sounds like a great way to speed things up.
Yeah.
Especially if the calculations are time-consuming.
Exactly. In our job scheduling solution, we define a recursive function that figures out the maximum profit achievable from a certain starting point, a particular job index.
Okay.
Inside this function, we use binary search, just like before, to find the next compatible gig, the one that doesn't overlap with the current gig.
Right. So we're still using binary search to efficiently navigate through our sorted list of gigs.
Precisely. Then, the function makes a recursive call to itself, exploring two possibilities, including the current gig in the schedule and excluding it.
Right.
For both possibilities, it recursively figures out the maximum profit achievable from the next compatible gig onwards.
So it's like a branching path where each decision to include or exclude a gig leads to a different potential outcome.
That's a great way to visualize it. And to avoid recalculating the profit for the same set of gigs over and over again, we use memoization. We store the result of each recursive call in a table. So if we encounter the same starting point again, we can simply retrieve the pre-calculated profit.
That makes a lot of sense. Memoization essentially turns our recursive function into a dynamic programming approach.
You got it.
By storing and reusing results.
And the combination of binary search and memoization makes this solution remarkably efficient.
Well, that was a whirlwind tour of algorithmic ingenuity. We've covered 5 incredibly clever solutions to the job scheduling problem.
It's awesome.
Each with its own unique approach and advantages.
It's a great example of how the same problem can be solved in multiple ways.
It is.
And choosing the right approach often depends on the specific constraints and requirements of the situation.
Absolutely. And highlights the importance of understanding different data structures and algorithmic techniques. They're like tools in a coder's toolbox.
Exactly.
Each suited for a different task.
Couldn't have said it better myself.
So, to our listeners there, keep those algorithmic brains sharp and don't be afraid to experiment with different approaches. You never know what brilliant solutions you might discover. Until next time on AI.Code.Cast, happy coding.